There is no fire on the sun. There is no natural fire anywhere else in the solar system that we know of. As far as we can tell, it exists only on Earth. Not because this planet is hotter, and not because we simply got lucky. The reason is much stranger, because before the first flame could exist, life had to spend billions of years rebuilding the air. That sounds wrong the moment you look up. The sun blinds your eyes, warms your skin, and throws eruptions into space that could swallow the Earth. If that is not fire, what is? The little blue flame under a kitchen skillet. The sun does not burn. Deep inside it, hydrogen nuclei are squeezed together so violently that they fuse and form helium. A small amount of mass becomes energy. No wood is consumed, no gasoline is mixed with oxygen, and no chemical flame is hiding behind the glare. The sun runs on nuclear fusion, a process as different from a campfire as a freight train is from a blood cell. Both move things. That is about where the similarity ends. Mercury is scorching, but it does not burn. Venus is hot enough to melt lead, but it does not burn. Io, the volcanic moon of Jupiter, throws molten material across its surface, but it does not burn. Titan has lakes and seas filled with hydrocarbons, and it does not burn. Earth is much colder. It is also the only known world that can catch fire. Lava creates the same confusion. When molten rock pours from a volcano, it glows, destroys buildings, and ignites anything combustible in its path. It looks like liquid fire. It is not. Lava is rock heated until it flows. When it reaches a house, the wood, insulation, paint, furniture, curtains, and roofing may burn. The lava provides the heat and lets the house do the chemistry. That difference sounds like the kind of correction a professor makes while the restaurant is already on fire. It is actually the entire story. Heat alone does not create flame. A fire needs fuel, an oxidizer, enough energy to begin the reaction, and conditions that allow that reaction to keep moving. Most of us learned a simple version in school. Fire needs fuel, oxygen, and heat. For a candle, a fireplace, a gas stove, or a dry forest, that explanation works. Chemistry is less loyal than the diagram suggests. Combustion does not always require oxygen. It requires an oxidizer, a substance that accepts electrons from the fuel and allows the reaction to release energy. On Earth, oxygen usually gets the job because it is already floating through the atmosphere, available everywhere, and does not need to be delivered in a steel tank. Other oxidizers exist. Hydrogen reacts explosively with fluorine. Metals can burn in chlorine. Magnesium can continue reacting in carbon dioxide by pulling oxygen away from the gas itself. That is why using the wrong extinguisher on burning magnesium can turn a manageable emergency into a live chemistry demonstration that nobody asked to attend. Rocket engineers once looked seriously at liquid fluorine. On paper, it was impressive. It reacted with enormous energy and promised excellent performance. In the real world, it was toxic, corrosive, difficult to store, and eager to attack nearly anything used to contain it. Fluorine was the employee who exceeded every production target while dissolving the factory. So fire without oxygen is possible. Building a stable planet around that chemistry is another matter. Free fluorine would not sit peacefully in an atmosphere. It would react with water, rock, metals, salts, and organic matter. Some powerful process would have to manufacture it continuously. Chlorine would be only slightly less hostile. A complex biosphere surrounded by either gas would need a very unusual chemistry and an excellent emergency room. Alien life may not resemble life on Earth. No law says every organism must use our proteins, our carbon chemistry, our metabolism, or our taste in atmospheric gases. But a reaction that can happen inside a laboratory flask is not the same thing as a planet that can remain stable for millions of years while forests grow and intelligent creatures argue about property taxes. Natural fire requires an entire system. There must be abundant fuel, an oxidizer that remains available, dry periods, sources of ignition, and a living world capable of rebuilding what burns. If the first flame consumes everything and nothing grows back, the planet did not develop a fire ecology. It had one terrible accident. Titan shows exactly how incomplete fuel can be. Saturn's largest moon has rivers, lakes, and seas of liquid methane and ethane. These are hydrocarbons, chemical relatives of the fuels used in furnaces, engines, power plants, ships, and backyard grills. Methane falls from the sky as rain. It drains through channels and collects in broad, dark seas. Titan looks like a gas station the size of a moon. It still cannot burn. The missing ingredient is an oxidizer. On Earth, a spark near a large methane leak is the beginning of a very short conversation with the fire department. On Titan, there is almost no free oxygen to support the reaction. The fuel remains cold and quiet. Imagine filling a garage with gasoline, cardboard boxes, dry lumber, old newspapers, and cotton rags, then removing every substance capable of supporting flame. The place looks ready for disaster. Chemically, it has been disarmed. This exposes one of the great asymmetries of the cosmos. Fuel is common. Hydrogen, methane, carbon compounds, ammonia, and organic molecules appear in comets, planetary atmospheres, interstellar clouds, moons, and disks around young stars. Free oxidizers that remain stable and abundant are far less common. The universe has no shortage of things that could burn. It rarely supplies the right air. Even on Earth, flame is not the rigid object it appears to be. Gravity shapes it. In a normal room, hot gases rise. Cooler air moves in from below, bringing fresh oxygen. This circulation stretches a candle flame upward and gives it the pointed shape everyone recognizes. The flame points toward the ceiling because gravity organizes the flow. NASA experiments in orbit remove that familiar arrangement. In microgravity, hot gases do not rise in the normal way. Oxygen reaches the flame slowly from every direction. The result is often a small blue sphere, dimmer, cooler, and more symmetrical than a flame on Earth. It looks less like a candle and more like a floating ghost trapped inside a glass box. Some space experiments have revealed an even stranger behavior. After a visible flame seems to go out, a cooler form of combustion can sometimes continue. These cool flames release less light and operate at lower temperatures, but the chemistry has not fully stopped. The fire becomes nearly invisible while it continues consuming fuel. A flame in orbit has no idea which way is up. That is not merely a visual trick. It changes how fuel mixes with oxygen, how soot forms, how heat moves, and when the reaction finally dies. Subscribe to the channel for more investigations where ordinary objects stop behaving normally the moment physics removes one familiar condition. A candle turns out to contain planetary history, atmospheric chemistry, and a piece of the search for alien civilization. The shape of a flame is not the central mystery, however. The real question is why Earth has a flame to reshape. Part of the answer was found nearly a mile underground in a former gold mine in South Dakota. Physicist Raymond Davis built one of the strangest machines in the history of astronomy. Deep inside the Homestake mine, shielded from cosmic radiation by thousands of feet of rock, he installed a tank containing about 100,000 gallons of perchloroethylene, a chemical once widely used in dry cleaning. Davis was not trying to clean a very large suit. He was waiting for solar neutrinos. Neutrinos are particles that barely interact with matter. They pass through walls, mountains, people, and most of the Earth as though the planet were made of thin fog. Every second, an enormous number of neutrinos from the sun pass through your body. They do not slow down for lunch. Very rarely, one of those neutrinos could strike a chlorine atom in Davis's tank and turn it into radioactive argon. Davis then had to extract and count a tiny number of argon atoms from an industrial tank of cleaning fluid. It was like trying to find several specific grains of salt after dumping them into a public swimming pool. The experiment detected neutrinos from the nuclear reactions inside the sun, but it found fewer than physicists expected. For years, the missing neutrinos created a serious problem. Was the experiment wrong? Was the model of the sun wrong? Was something happening to the particles during their trip? Later experiments showed that neutrinos can change from one type into another. Davis's detector was sensitive mainly to one type, so many of the particles had not disappeared. They had changed identity on the way to Earth. The mystery strengthened the nuclear model of the sun instead of destroying it. Those particles came from reactions in the solar core. They were evidence from inside the engine. They did not carry news of a fire. They carried the signature of nuclear fusion. The surface of the sun does contain plasma, electric currents, and magnetic fields. Sunspots, solar flares, coronal loops, and eruptions are deeply connected to magnetism. This is the part emphasized by supporters of the electric universe, including Wallace Thornhill and Donald Scott. In its mildest form, the claim is uncontroversial. Electricity and magnetism matter enormously in space plasmas. The stronger version argues that external cosmic currents provide most of the sun's energy and that nuclear fusion is not its main engine. That version does not have a quantitative model capable of explaining stellar lifetimes, internal temperatures, the brightness of different stars, the neutrino measurements, and the way entire stellar populations change over time. Finding electrical wiring in a house does not prove that the foundation, plumbing, furnace, roof, and walls are imaginary. Another suspicion appears whenever people say the sunlight feels harsher than it did decades ago. Many adults remember staying outside for hours as children and compare that memory with skin that now reddens quickly. Some say the sun looks whiter, others believe the star itself has changed. Measurements do not show a huge continuous increase in solar output. The amount of ultraviolet radiation reaching the skin depends on more than the star. Ozone, clouds, aerosols, altitude, humidity, water, pale concrete, snow, and sand all change exposure. Cleaner air can allow more sunlight to reach the ground. Drought can reduce cloud cover. Water and bright surfaces reflect radiation. Some medications make skin more sensitive. Age quietly joins the meeting and waits until the bill arrives. The experience can be real without the sun becoming a different star. Online communities connect these observations to chemtrails, secret geoengineering programs, or changes in Earth's magnetic field. Researchers really do discuss proposals for reflecting a small fraction of sunlight to reduce warming. That fact does not prove that aircraft trails are part of a hidden global system for controlling the sky. A real scientific debate can become fuel for a much larger story. Fire is not the only thing that spreads when the conditions are right. Early Earth had a very different atmosphere. The oceans existed, volcanoes erupted, lightning crossed the sky. Life was already present, yet oxygen was scarce, and for many organisms, it was toxic. The first ecosystems used chemical pathways based on hydrogen, sulfur, iron, methane, and other available substances. They did not breathe oxygen. Some modern organisms still live this way in deep sediments, swamps, animal intestines, and parts of the crust. There is even a microscopic animal parasite called Henneguia salminicola that has lost much of the usual genetic machinery associated with oxygen-based mitochondrial respiration. It lives inside salmon tissue and reminds us that life and oxygen are not legally married. For most of Earth's history, the planet was alive without an atmosphere that a human could breathe. Then, microorganisms related to modern cyanobacteria learned to use sunlight to build organic matter. They took in water and carbon dioxide, stored energy, and released oxygen as waste. Humans treat oxygen as the valuable part of the air. To those microbes, it was the trash left over after dinner. At first, oceans and rocks absorbed almost everything. Oxygen reacted with dissolved iron and created enormous mineral deposits. The planet was rusting. Microbes kept producing the gas while Earth stored it in rock, like a family filling a garage with empty boxes because somebody may need them someday. Eventually, the major chemical sinks began to fill. Oxygen entered the atmosphere and transformed the planet. Many anaerobic organisms lost their environment. Some retreated into oxygen-poor places. Others evolved protection. A few learned to use the new poison. Aerobic respiration can extract far more usable energy from food than many anaerobic pathways. This does not prove that complex life is impossible without oxygen. It shows the route Earth took to support rapid movement, Large bodies, elaborate senses, nervous systems, and energy-hungry brains. A microbial waste product became biological fuel. Much later, it would become the oxidizer for fire. The danger of oxygen is easy to underestimate because we live inside a diluted atmosphere. Apollo 1 revealed how quickly the rules change when the concentration rises. During a ground test in 1967, astronauts Gus Grissom, Ed White, and Roger Chaffee sat inside a spacecraft cabin filled with pure oxygen at pressure slightly above normal sea level pressure. A spark started a fire. Materials that seemed manageable in ordinary air burned violently in the oxygen-rich cabin. The flames spread through the spacecraft in seconds. The crew could not open the inward opening hatch against the cabin pressure. After the disaster, NASA changed wiring, materials, procedures, hatch design, and the atmospheric mixture used during ground operations. Engineers conducted large-scale flammability tests because oxygen does more than make an existing fire brighter. It can change which materials behave like fuel in the first place. A strip of fabric, a piece of plastic, or insulation that burns reluctantly in normal air can become dangerous in a pure oxygen environment. The difference is not intelligence, bravery, or engineering ambition. It is atmosphere. Fire lives inside a window. Too little oxygen, and flame struggles to spread. Too much, and ordinary surroundings begin acting like a warehouse full of kindling. Long before anyone could explain that chemistry, human cultures treated fire as something alive. It moved, consumed food, breathed air, grew, weakened, and died. Feed it wood and protect it from wind, and it survived. Neglect it, and darkness returned. Greek tradition said Prometheus stole fire from the gods. The gift was larger than warmth. It gave human beings the power to change matter. In Vedic tradition, Agni connected the household flame, lightning, ritual, and the heavens. Zoroastrian tradition treated fire as a visible sign of purity and order. Alchemists used controlled heat while searching for both material transformation and inner transformation. They did not know about electrons or oxidizers. They understood something practical. Fire takes matter and returns it altered. Supporters of ancient astronaut theories interpret those stories literally. Erich von Däniken and other writers propose that gods who brought fire may preserve distorted memories of advanced visitors who transferred technology to early humans. In that version, fire may mean more than a burning branch. It could represent cooking, pottery, metallurgy, weapons, or an unknown energy source described in the only language ancient people possessed. There is no direct archaeological evidence for that interpretation. Human control of fire appears gradual. Natural flames were collected, embers were preserved, ignition techniques developed, hearths improved, and furnaces appeared much later. Visitors capable of crossing interstellar space would have chosen an unusually slow educational program. First, warm meat. Then wait several 100,000 years for a decent kiln. The theory remains attractive because the effect of fire was so enormous. It feels less like discovering a tool and more like receiving permission to redesign matter. Some indigenous peoples of North America developed a different relationship with fire, one based not on stealing it from gods, but on using it as landscape medicine. For generations, communities including the Karuk and Yurok peoples of Northern California used carefully timed burns to shape forests, improve food plants, support wildlife, clear travel routes, and reduce dangerous fuel buildup. Fire was not treated as a force that should always be eliminated. It was a process that could be guided. Karuk ecologist and fire practitioner Frank Kanawha Lake has described cultural burning as part of a living relationship with the land. Small, low-intensity burns can restore plants used for food, basketry, medicine, and ceremony. The difference between useful fire and catastrophic fire may be timing, weather, fuel, frequency, and who understands the landscape. Giant sequoias carry the same lesson in their biology. Fire can dry and open cones, clear litter, expose mineral soil, and create conditions where seedlings can establish. Remove fire completely, and the forest changes. Allow severe fires to build under extreme conditions, and even ancient giants can die. A sequoia does not need any fire at any time. It needs the right fire in the right system. That distinction took American land management a long time to relearn. For much of the 20th century, the public message was simple. Fire was the enemy. Put it out. Decades of suppression allowed dead wood and dense vegetation to accumulate in many forests. When drought, heat, wind, and ignition arrived together, the result could be far more destructive than the smaller fires that once moved through regularly. The problem was never simply whether fire existed. The problem was whether a living system had learned to live with it. Humans had to learn the same lesson at a smaller scale. Our ancestors did not invent fire. They found it after lightning strikes, volcanic events, and natural burns. At first, a flame may have been something to preserve. Lose the embers, and there was no hardware store open until midnight. Keeping fire changed the night. It provided warmth, light, protection, more working time, and a place for people to gather. It also changed food. Heat breaks down cellular structures, softens tissue, kills many pathogens, and makes some energy easier to absorb. Cooking reduces the time and effort required for chewing and digestion. Harvard anthropologist Richard Wrangham has argued that cooking played an important role in human evolution. Easier access to calories may have helped support a large and expensive brain. The idea remains debated. Cooking alone did not create humanity. Hunting, cooperation, social competition, climate, tools, and changing food supplies all mattered. Fire still changed the energy budget of dinner. The human brain consumes a remarkable share of the body's energy, even when its owner is standing in the kitchen looking for the glasses already sitting on top of his head. Cooked food may have helped pay that bill. The larger technological transformation began when people stopped merely keeping a flame alive and began designing the space around it. An open fire produces heat. A furnace concentrates heat, controls airflow, changes the chemical environment, and holds temperature. Charcoal can burn hotter than ordinary wood. Bellows deliver more oxygen. Walls prevent energy from escaping. At that point, the flame becomes part of a machine. Clay becomes pottery that does not dissolve in the next rain. Sand and other minerals become glass. Ore releases metal. Limestone becomes lime. Pigments change color. Materials that nature keeps separated can be combined into objects that never existed before. A backyard fire pit and a steel mill are related, but only in the way a bicycle and a moon rocket are related. The difference lies in control. Metallurgy is not a matter of dropping a rock into a fire and waiting for a sword to come out. Ore must be prepared. Airflow must be managed. Impurities must be separated. Temperature must be held. The metal must be shaped before it becomes useful. Every modern object carries that ancestry. The glass in a screen, the copper in wiring, the aluminum in an aircraft, the steel in a bridge, the ceramics in electronics, and the purified silicon in a computer all descend from controlled heat. A smartphone looks digital. Its family comes from furnaces. That connection led American astrophysicist Adam Frank and Italian astrophysicist Amedeo Balbi to ask whether fire could be a cosmic bottleneck. A technosphere is the complete system of technology built around a civilization. Roads, power grids, factories, radios, satellites, data centers, engines, and the waste products visible from a distance all belong to it. Frank and Balbi pointed to a gap between the amount of oxygen that may support complex organisms and the amount needed for reliable open combustion. In an Earth-like atmosphere, fire useful for metallurgy becomes increasingly difficult as oxygen falls toward levels below roughly 18%. There is no universal switch. Pressure, humidity, temperature, and fuel type all matter. Dry grass and wet timber do not behave the same way. The broader problem remains. A world might have enough oxygen for animals and too little for a dependable furnace. Its inhabitants could understand the motion of planets but lack glass for a precise telescope. They might design machines without the metals needed to build them. Mathematics, music, law, memory, and philosophy could develop while iron remained trapped in rock. They would not be less intelligent. They would be trapped by the air. Astrobiologists Manasvi Lingam, Amedeo Balbi, and Swadesh Mahajan have considered the same problem on ocean worlds. A planet covered by water may provide a stable environment protected from radiation. It may also make open fire nearly useless. Hydrothermal vents provide heat and chemical energy, but they are not free industrial furnaces. Temperatures vary, materials disperse, water interferes with reactions, and nobody can ask the volcano to turn the heat down because the batch is being ruined. Building metallurgy underwater would be like operating a pizza oven at the bottom of a swimming pool. The recipe may be excellent. The room has already voted against it. A marine civilization might follow a biological route. Organisms grow bone, shell, teeth, wood, fibers, and complex structures without blast furnaces. Electric fish produce voltage without copper coils. Living systems process information without silicon chips. One can imagine cultivated machines, living buildings, biological lights, and organic computing. Physics does not forbid such a civilization. We have never observed one. The only technological path known to work passed through flame. That possibility connects fire to the Great Filter. Economist Robin Hanson used that term for one or more extremely difficult steps between dead matter and a civilization capable of leaving a cosmic trace. The idea addresses the problem associated with physicist Enrico Fermi. If the galaxy contains so many stars and has existed for so long, where is everybody? Perhaps life rarely begins. Perhaps complex cells are almost impossible. Perhaps intelligence destroys itself. Or perhaps some minds reach the edge of technology and discover that their atmosphere refuses to cooperate. The Great Filter may stand in front of the first furnace. Such beings could know that stars exist while the stars never learn that they exist. They would have thoughts, but no transmitter. Without workable metals, glass, ceramics, controlled energy, and precision instruments, the greatest message in their history would remain a conversation around a table. The ancient astronaut solution offers a shortcut. An advanced visitor could deliver finished machines and technical knowledge to a civilization unable to develop them alone. The problem is maintenance. A device without replacement parts, factories, trained workers, energy, and materials becomes a sacred object after the first serious malfunction. Priests can argue over the button. Chemistry still sends the invoice. The decisive evidence that Earth crossed the fire barrier does not come from mythology or speculation. It appears in black fragments smaller than a fingernail. Researchers Ian Glasspool and Robert Gastaldo examined carbonized remains from Wales and Poland. Under a microscope, the fragments preserved biological structures altered by heat. They were not simply dark minerals. They were burned vegetation from the Silurian period, roughly 430 million years ago. At that time, Earth did not yet have forests like modern forests. Small land plants and other low vegetation had begun producing enough dry organic material to act as fuel. The charcoal was the signature of a planetary transition. Life, lightning, volcanoes, and rising oxygen had existed separately. Now they came together. A spark reached dry biological material in air capable of supporting combustion. The reaction moved from one fragment to the next. Earth experienced its first known natural fires. Paleobotanist Andrew Scott spent much of his career reading ancient fire history in fossil charcoal. The presence of charcoal in rock places limits on the oxygen level of the atmosphere in which it formed. If vegetation burned and the flame spread, the air had to allow it. This leads to the idea of a fire window. At low oxygen levels, flame spreads poorly. As oxygen rises, more materials become combustible, wetter fuels become vulnerable, and ignition becomes easier. There is no single percentage that applies to every plant, pressure, temperature, or humidity. A dry field and a soaked log do not negotiate with fire on the same terms. But Earth had to enter a range where natural fires could occur and controlled combustion could eventually become reliable. Scott and Glasspool read that threshold in the distant past. Frank and Balbi look at the same chemistry as a barrier in the future of technological life. The atmosphere decides what can burn. Around 300 million years ago, during the Carboniferous period, oxygen may have risen far above modern levels. Some models suggest more than 26%, perhaps approaching 30% during certain intervals. Fossil charcoal became abundant. Vegetation burned more easily. The same atmosphere supported unusually large arthropods, including dragonfly relatives with wingspans comparable to birds and Arthropleura, a millipede relative that could grow longer than a person. High oxygen was not the only reason for their size. Climate, food, competition, and anatomy all mattered. Their respiratory systems still benefited from richer air. The atmosphere was generous to giant arthropods. It was generous to flame as well. Modern air contains about 21% oxygen. That number was not selected by a cosmic engineer. It results from a shifting balance among photosynthesis, respiration, decomposition, wildfire, oceans, volcanoes, burial of carbon, and reactions with rock. Earth is not a precision thermostat. It is more like an old house where the furnace, attic, windows, insulation, and one relative who keeps touching the controls all affect the temperature, while the instruction manual disappeared years ago. Once fire entered ecosystems, evolution began using it. Some plants developed thick bark, others regrow from underground tissues. Certain cones release seeds after heating. Some seeds germinate better when fire weakens their protective coating. Fire can remove competitors, release nutrients, and create open ground. It kills individuals while maintaining the landscape on which their species depends. Some insects can detect infrared radiation and fly toward recently burned trees to lay eggs. Where humans see an evacuation zone, they see available real estate. In northern Australia, Indigenous knowledge describes something stranger. Geographer Mark Bonta and researcher Robert Gosford collected reports of black kites, whistling kites, and brown falcons carrying burning sticks. According to witnesses, a bird may pick up a smoldering branch and drop it beyond the existing fire line. Dry grass ignites. Small animals flee cover. The hunting area expands. Bonta and Gosford gathered accounts from indigenous communities and experienced field workers. The reports are consistent, but direct observations remain rare. Proving an animal's intention is difficult. The behavior may be strategic, or some events may be interpreted too confidently. The scientific file remains open. If the birds spread fire deliberately, humans are not the only animals using flame as a tool. We are the animal that turned a burning stick into a planetary industry. Fire also does something that appears to contradict its nature. It destroys evidence and preserves it. In the year 79, the eruption of Mount Vesuvius buried the Roman town of Herculaneum. A hot surge carbonized hundreds of scrolls stored in a villa. The heat turned them into black cylinders so fragile that trying to open them could reduce them to powder. For nearly 2,000 years, they looked like books that had been completely destroyed. Modern X-ray imaging, three-dimensional scanning, and computer analysis can reveal writing inside some of the still-rolled scrolls without physically opening them. Ink and letters hidden inside carbonized layers are becoming readable. The heat that erased a city also sealed a library. Fire can destroy tissue, buildings, forests, and archives, then create charcoal, stop decay, preserve microscopic structure, and turn a catastrophe into a document waiting for a technology that does not yet exist. That is why fossil charcoal matters. Fire does not merely remove the past. Under the right conditions, it signs its name across it. Astronomers looking at exoplanets search for oxygen because it can be associated with life. Oxygen alone is not proof. Starlight can split water molecules, hydrogen can escape into space, and oxygen can remain behind on a lifeless world. The whole atmosphere must be considered. Water, oxygen, ozone, methane, carbon dioxide, seasonal changes, and combinations of gases that should not coexist for long may provide a stronger case. Evidence of widespread natural fire would add something important. It would suggest abundant fuel, an available oxidizer, a surface that sometimes becomes dry, sources of ignition, and an atmosphere that allows the reaction to spread. If life produced the fuel, fire could become an indirect biosignature, not a confession. A very interesting fingerprint. A technological civilization might leave different signs: industrial gases, artificial light, radio transmissions, unusual heat, or compounds that natural processes rarely produce are called technosignatures. Natural fire would say that a planet can burn. A technosignature might say that somebody has learned when, where, and why to release energy. An advanced civilization may eventually move away from visible flame. Solar panels do not burn. Wind turbines do not burn. A nuclear reactor is not a campfire. Technology can begin with fire and later hide it inside engines, turbines, laboratories, power grids, and industrial systems. The latter may be left behind. Its steps remain in metal. Human beings also learned to burn ancient life. Coal, oil, and natural gas contain carbon accumulated and transformed over geological time. The planet filled the warehouse for millions of years. We found the key and decided to empty it before dinner. Fire made cooking, pottery, glass, metalworking, industry, and spaceflight possible. It also made incendiary weapons, pollution, and rapid carbon release possible. In the myth of Prometheus, the gift brings punishment. That does not mean the Greeks understood modern climate science. It means they recognized that a power capable of transforming the world usually arrives with a price. Flame protects a home and destroys a town. It prepares food and burns a crop. It produces a tool and a weapon. It lights the darkness and signals danger. Fire has no intention. It increases the reach of ours. Wildfires are becoming more destructive in many regions because temperature, humidity, vegetation, drought, wind, and fuel accumulation are changing. The chemistry of combustion has not received an update. The environment is setting a better table. Peat fires can smolder below the ground, survive cold weather, and return later. They do not always produce dramatic walls of flame. The land quietly consumes its own carbon reserve like a bank account losing money overnight without sending an alert. We do not know every possible path to civilization. An ocean species may cultivate biological technology. An alien atmosphere may support another useful reaction. A world without flame may exploit geothermal energy, catalysts, living materials, or a method no human has imagined. We do know what happened here. A star supplied energy without burning. Life learned to capture it. Microbes transformed the oceans and atmosphere. Plants built fuel on land. Oxygen entered the range where flame could spread. Lightning completed the circuit. Hundreds of millions of years later, a human picked up a burning branch and declared ownership of fire. Perhaps the ancient stories were wrong only about the identity of the giver. Fire did not have to be stolen from gods, and it did not require visitors from the stars. The gift was prepared long before humans appeared. An entire planet built it. That may be why the most important boundary in the cosmos does not separate dead worlds from living ones. It may run between planets where life learns to think and those rare worlds where thought finds enough fuel, enough oxidizer, and enough time to light the first flame.